Good morning, everybody. My name is Matthias-Fresacher, and today I'm going to tell you about the Congruence Lattices of Finite twisted Brauer and Temperley-Lieb monoids. Before I begin, a quick thank you for inviting me to speak in this seminar, and I've really enjoyed my time here at the University of York. So let's get into it with an overview of what I will be covering today. So as the title suggests, that's going to be two things: diagram monoids and congruences. On the monoid side, I'm going to go through some motivation as to why we might care, and then define our Brauer and Temperley-Lieb monoids that we're going to be interested in, but I'm going to modify them slightly to be in a twisted setting. On the congruent side, I'm going to go through what they are, give some examples and define the ones we are going to need, and again explain why we might care about these in the first place. That will allow me to state the theorem I was able to prove, well in fact two theorems over the last couple of years, give a little bit of an outline of that proof. That will nicely lead into some of the other output this work has resulted in, and as well as the possible future directions for this line of research. And throughout this talk, there are two things I would like you to take away, and that is that the technical maths has been done by pictures on two levels. One at the diagram level, where we look at specific diagrams via the diagram representations of them as graphs, and at the congruence level, where we make use of an egg box diagram to simplify the technical definitions of the congruences. So let's get into it with the monoids we're going to be covering. So an example motivation for a use case for these monoids comes from statistical thermodynamics. And here the atomic interactions between atoms is modeled by matrices. Specifically, these matrices are elements of an algebra, and this algebra is in fact a twisted semigroup algebra where the semigroup is the Brauer monoid. This whole construction is typically called the Brauer algebra. So we can see if we get a better understanding of the Brauer monoid, in this case we get a better understanding of statistical thermodynamics. There are other examples of the use case for these monoids. They are in the fields of biology, representation theory, invariant theory, and knot theory, just to name a few. So let's get into the technical details. What is a monoid? Well, it's a set together with a binary operation, usually denoted by multiplication, and it has to be associative. So in essence, if we're multiplying three things together, the order doesn't matter. We don't need to worry about brackets. If we just have this, we have a semigroup. If we now add in an identity element, then we have our monoid. Specifically, we're not going to be interested in just any monoid. We're going to be looking at the Brauer monoid Bn. And it has as its elements the Brauer diagrams. These are usually denoted by two rows of vertices numbered from left to right, with the bottom row being dashed numbers. And we draw some edges. We might have some upper non-transversal edges, lower non-transversal edges, or some transversal edges linking the top and the bottom rows. The Brauer diagram has the condition that every vertex must be connected to exactly one other vertex. We're also going to be looking at the Temperley-Lieb monoid, TLN, and this is sometimes referred to as the Jones monoid. And for those of you that are paying close attention, yes, this is the same Jones as the paper that I referenced in the motivating example on the previous slide. This is actually a submonoid of the Brauer monoid, so its diagrams have the extra condition that edges are not allowed to cross like they do up here. The graph must be planar in some sense, and the some sense here is that edges are only allowed to be within the rectangle of our vertices. We're not allowed to draw edges around the outside. Now this is the graphical representation of these diagrams, sort of as graphs, but strictly speaking, the more formal and algebraic construction is to think of them as a partition of this particular set. And then the translation to go between these two is that each element in our partition here, so each block, must correspond to a connected component in our graph. And because this is a partition, this is where the name, the partition monoid Pn, comes from. And the partition monoid is sort of the overarching monoid of all of the different diagram monoids. So Brauer and Temperley-Lieb, they're both submonoids of the partition monoid. So this is an arbitrary partition diagram example. So here we can see we might have blocks of size 3, we might have vertices that are not connected to anything. Basically, there's no rules on our diagram. And it's important to note here that the graphical representation is no longer unique. Because, for example, if I draw in this extra edge here, the connected components of this graph hasn't changed, and hence the partition hasn't changed, so our diagram hasn't changed. But for Temperley-Lieb and Brauer, our graphical representations are unique. Now that I've told you about the partition monoid, I basically would like you to forget about it again until almost at the end of the slide, of the presentation rather, where we'll make a brief reappearance. And the reason for that is because the definitions that I'm about to go through, they're phrased in terms of a Brauer monoid, and some of them are slightly simpler than the equivalent definition for the partition monoid. And obviously, if I define things for the Brauer, considering Temperley-Lieb as a submonoid, Temperley-Lieb has well-defined definitions. We can talk about the degree of an entire monoid, and this simply counts the number of vertices in our rows of vertices in our graphical representation. So all of these diagrams belong to a monoid of degree 5. We can also talk about the rank of a specific diagram, and this counts the number of transversal edges. So here we have 1, 2, 3 transversal edges that link the top and the bottom row. So this diagram has got rank 3. This one, we only have 1 such edge. This diagram has got rank 1. And for the Brauer monoid, it holds that the rank and the degree always share the same parity. And we can see this fairly easily that, for example, here we have a non-transversal, because it has to be always 2 vertices that are linked together. If we sort of remove that, that removes 2 vertices. So the parity of our original number of vertices in our row and the number of transversals stays the same. Concatenation, that's the multiplication operation of our monoid. For those of you that are visual-based learners, this is an animation of that procedure in action. For everybody else, I'm going to make use of this intermediary step to show how we end up at the concatenated diagram. So let's go through the steps in detail for calculating alpha times beta. First, we position the 2 diagrams directly on top of each other, and then we draw that red vertical in-between edges here. We then remove these 2 inner rows of vertices, and we remove any loops that are created. So a loop is any collection of edges that are not connected to the top or the bottom row of vertices. And this idea of a loop is going to be important, so just keep it in mind for later on. And then we tidy up what we have. So we're just going to squish our 2 rows of vertices back to normal size. We can see we have a connection from vertex 2 to number 4. So we just draw a clean edge here and basically just tidy it up. We can sort of see fairly easily from the picture that this operation is in fact associative, and that we have an identity diagram, specifically just all vertical edges. And we can also see that this operation is not necessarily commutative. That now brings me to the twisted variety. So that was the non-twisted monoids. Now we're going to look at the twisted versions of these monoids. And here, roughly speaking, we need to keep track of the loops. So you can think of the twisted Brauer monoid as being your standard Brauer monoid, Cartesian product, the natural numbers. And that natural number, roughly speaking, well, in fact it is, the number of loops present in our diagram. Obviously, this is going to be an infinite monoid, so it is a little bit tricky to work with. We do need to modify our concatenation from the previous slide. And pictorially, if you recall our intermediary step, well, before we go anywhere, we need to associate that natural number, so the number of loops. So suppose in this example that alpha just has 1 loop, and suppose beta in this example has got 3 loops. For ease of notation, I'm just going to write in red the number of loops associated to each diagram. So then to calculate the concatenated diagram, basically all we do is we count up how many loops have we got. So we do concatenation on the diagram as we did before, so nothing changed in terms of the diagram that we have here, but now we need to count the loops. So we have 1 loop from alpha, we have 2 loops that are created during the concatenation process, and beta had 3 loops. So 1 plus 2 plus 3, that gives us 6 loops in alpha beta. Formally speaking, so if we have 2 twisted diagrams, so the diagram and that natural number, the product is just going to be your normal concatenation of diagrams, and then we add up the number of loops. So the number of loops in alpha plus beta, and then phi simply counts the number of loops that are created in the concatenation process. So in this example, that was 2. We can also define a D-twisted Brauer monoid. And this is where, instead of making use of all of the natural numbers, I'm just going to go up to some number D. And for this to still be a monoid, we also need to include a 0 element here. Clearly, this is going to be now a finite monoid and is going to be much easier to work with. Now that 0 element, we think of it as a diagram, even though it isn't actually a diagram. It's also not a partition, so we can't draw it, but we just pretend that it does exist as such. And obviously, being a 0, anything multiplied by it is just going to be 0. And also, sort of just to ease the notation, we, by definition, define the rank of the 0 diagram to be negative infinity, and we consider a negative infinity to be both odd and even. So the concatenation, well, we need to modify that again slightly in this D-twisted setting. So we're going to have the product of 2 diagrams is equal to 0 if this quantity is bigger than D. So essentially this parameter D is the maximum number of loops that we are permitted. And if at any point during a concatenation process we exceed that maximum number, well, then just by definition we have the 0 diagram. A special case of this is when D is equal to 0, and that is going to be the focus of this talk. So if you sort of got lost, what I'm about to say is the important bit to keep in mind for the rest of the talk. So here, the elements of the 0 twisted Brauer monoid, you can think of them, it's not quite strictly speaking equals, as all of your normal Brauer diagrams with the addition of that 0 diagram. And in terms of concatenation, it is the ordinary concatenation of diagrams with the extra condition that as soon as any loop is created, so here we already have 2 loops, then just by definition we have the 0 diagram. For those of you that are familiar with it, this does correspond to a Brauer, respectively, Temperley-Lieb algebra with a twisting coefficient equaling to 0. That now allows me to move on to the congruences we are going to need. So let's define what a congruence is. Well, it's an equivalence relation, usually denoted by sigma, on our set of diagrams. But it must be compatible with concatenation. And by that we mean if I take a diagram alpha that is congruent to a diagram beta, if I multiply on the right by any other diagram gamma, that pair must still be congruent. And likewise, I want the same condition to hold for on the left. Some easy examples of the universal congruence, where just everything is congruent to everything else. We can quite easily see that this is, in fact, an equivalence relation, and that the congruence relation holds. Another easy example is the trivial congruence, where everything is congruent only to itself. Again, fairly easy to see this as an equivalence relation, and that the congruence condition would hold. Sort of in between these two extremes, we're going to get a congruence lattice. So roughly speaking, we would have the trivial congruence at the bottom, we have the universal congruence at the top, and all sorts of different congruences sitting in between these two extremes. And we can think of sort of this lattice as in 2 ways. So if I take some monoid and I look at the congruences, so that's going to be a set, and I can order this set, so we have a partial ordering, using subset inclusion. So for example, in here, sigma 10 would be a strict subset of sigma 11. Alternatively, we can think of this in a more algebraic setting as a lattice, where we have 2 operations, the join and the intersect. So for example, the join is an example here. So sigma 6 would be the join of sigma 4 and sigma 5. So the join essentially makes the congruence a bit bigger. And so the opposite is the intersect. So for example, sigma 3 here is the intersection of sigma 4 and sigma 5. And this essentially makes the congruence a bit smaller. If I were to take an arbitrary semigroup or monoid and look at its congruence lattice, chances are it's horrendously complicated and really huge, too messy for it to be of any use at all, really. But it's a remarkable fact that for diagram monoids, these congruence lattices are extremely simple and can be as simple as just a chain, obviously the simplest lattice you can have. Another ingredient we're going to need is the notion of a principal congruence. And this is where we take a pair alpha and beta, and we'll look at what's the smallest congruence that contains that pair. Why do we care about congruences to begin with? Well, congruences govern quotients in exactly the same way that ideals are really important for rings, or normal subgroups are important for groups. And in fact, if you go back to the motivating example, it's usually not the entire Brauer monoid that appears in those uses. It's actually a quotient of our Brauer monoid. And because of this, we really need to understand the congruences to be able to understand those quotient monoids. We're going to need to know what the Green's relations are for our monoid. And recall that the Green's relations are some equivalence relations on our set of diagrams. We have the R relation, and two diagrams are related if their top rows are the same. And by that we mean if a vertex is part of a transversal edge, then in the other diagram it is also part of a transversal edge. And similarly, non-transversal vertices are non-transversal in both diagrams. But it's really important to note here, for non-transversal vertices, the actual edge must be the same across both diagrams. That's clearly not the case here, and that is why these two diagrams are not R-related. We also have the L relation, so analogously, this is that the bottom row of the two diagrams have to be the same. The H relation, well, that's the intersection of R and L, so logically that would mean both the top and the bottom row of our diagrams have to be the same. The H classes are in bijection with the symmetric group of that rank. So we can see that here. We have rank 2, and we have the two elements of the symmetric 2 group appearing. And this bijection is going to be really important for the work that we're about to look at. Also important is going to be that for Temperley-Lieb, the H relation is the trivial relation. And that comes back to no crossings allowed. So obviously here we have a crossing, this is not allowed. And we can sort of see the only bits of the symmetric group where we don't have any crossings is the identity element. That's only one. Hence H is trivial in Temperley-Lieb. Again, keep that in mind for later on. D, well, that's the join of R and L. And the D classes here are all the diagrams with a given rank. And the ideals are all the diagrams of a given rank or less. The final ingredient we're going to need is the hat map. This is defined for even degree. And essentially all it does is it pairs up transversals that are next to each other and it annihilates them, so replaces them with two non-transversals. And so just the obvious way that you would expect that to be done. We're going to need a group action. And for that, we're going to make use of this bijection between a H class and the symmetric group. So let's just call that F. Now to define this group action, I'm going to need some ingredients. First, I'm going to take some diagram, say alpha, and I'm going to take a permutation pi from our symmetric group. And then I can define alpha being acted upon by a permutation on the right. And yes, you can define this on the left, but we're just going to need one direction for this. So how could we do this? Well, algebraically, we could start off with our alpha. We can use our bijection to map it into a group element. There I can then multiply the group element with my permutation pi. That's going to be another group element, which I can then use my bijection to go back into some diagram. I can also do this graphically. So let's consider an example diagram here. We have rank 4, so we need a permutation from the symmetric 4 group. This is a perfectly good example. And then I calculate my group action by drawing my alpha, and underneath I draw my permutation. But I need to be careful here. I need to make sure that for my permutation, the vertices match up to the ones that are actually transversal in that bottom row, which obviously means there's going to be some blank bits somewhere. And those blank bits, well, I'm just going to put in vertical edges, essentially sort of the identity, so I'm not going to do anything there. And then to calculate my group action, I just do concatenation on these two diagrams. So we see that the concatenated diagram, so alpha acted upon by pi, is basically just going to be our two transversals having been crossed over, which makes sense considering that's exactly what our permutation is. So it's fairly easy to see that it holds that when we apply this group action, we stay within the same D class, our rank doesn't change, and in fact we stay in the same H class. And this property that we're in the same H class is also going to be important for later. So that now allows me to define the congruences we are going to need. And I'm going to make use of this, explain these through an egg box diagram. And the asterisk here is because the number of rows and columns in the middle here is entirely made up. So we're going to look at the zero twisted Brauer monoid of degree 6. And recall, what is an egg box diagram? Well, essentially you can think of it as just being full of dots, where every dot represents an element or diagram in our monoid. So at the bottom we would have our 0 diagram, then we have D0, so all the diagrams of rank 0 sitting here, all the diagrams of rank 2, all the diagrams of rank 4, all the diagrams of rank 6, but that's the symmetric 6 group. And then recall, if two diagrams are in the same row, then they're going to be R related. Analogously, if they're in the same column, they're going to be L related. Hence, if they're actually within the same box, then they are H related. So if we just sort of zoom in on, say, this top corner of the D2 class, well, D2, rank 2, so you can see all of our diagrams have rank 2. And within a H class, well, we only have symmetric 2 group, that's 2 elements, so we have 2 diagrams in each. And we can sort of see we have the symmetric 2 group appearing in all of these. And recall, if we go along a row, we are R related, so all of these diagrams have the same top row. And likewise, if we go down in a column, diagrams have to be L related, so all of these have the same bottom row. And obviously this repeats, sort of this pattern and structure holds for the whole egg box diagram. The first congruence we're going to look at are the Riesz congruences, and this is where we collapse the P ideal to a single representative. So pictorially, if we look at an example of, say, R2, everything that's in the second ideal, so rank 2 or less, so everything in red here, that's just going to get collapsed to a single representative. And over here, I'm going to have some example diagrams. These are always going to be the largest diagram, so the largest pair possible. Both these diagrams are of rank 2, so obviously they're going to be related by R2. Next, we have new N, where N is some normal subgroup of the symmetric group. And you will notice it's in red, and that's because it's not actually a congruence. It's only an equivalence class, but it's going to be an important ingredient for the other congruences, so we still need to know what it is. And what is it? Well, if we're H related, recall that gives us that bijection into the symmetric group and that group action. And essentially it's saying, if I can go from alpha to beta via some group action in that normal subgroup that I chose, then we are nu related. So for example, let's look at the alternating 4 group. So in D4, within a H class, well, I have the alternating 4 group that's got odd and even elements. I'm going to get 2 equivalence classes, so blue and yellow, for example. And this gets repeated across each H class, but it's important to note that the equivalence classes are different across each of the H classes. And likewise here we can see if I apply in fact sort of the inverse of this group element, this free permutation, that sits in the alternating 4 group, and I can get back to the identity, hence these two are related by nu. So that allows us to define the group-based congruences, where we take the Riesz congruence underneath, and sort of this is the missing bit that turns this equivalence relation into a congruence, and then we just have nu. So pictorially, if we continue with the alternating 4 group, everything of rank 2 is collapsed, and then we have this partitioning of the H classes into 2 equivalence classes, as you saw before. And likewise, the 2 diagrams, well, they were nu related, so obviously they're going to be R related for that same group. A different example would be the symmetric 4 group. And here again, we collapse our second ideal, but this time the group action is much more encompassing. In fact, I can go from anywhere to anywhere if I have the whole symmetric foregroup available to me, and as such, the whole H class in rank 4 gets collapsed. And we can see that here, this diagram is clearly not a part of the alternating foregroup, so I need the entire symmetric foregroup to go back from here to the identity element there. We then have some lambda-based congruences, starting with lambda up. And this is where we take R as 2 as a starting point, as well as if we're R related in rank 2, we can also be congruent if our hats are the same. So pictorially, we collapse our zeroth ideal and H classes in D2, that's RS2. And then if we're R related, so in the same row, if our hats are the same, we're also congruent. So potentially some of these H classes get identified across a row. And this gets repeated across each row, but again, important to note, the equivalence classes are different for each row. So here we can check these two diagrams. They're both of rank 2. They are R related, so their top rows are the same. Their hats are also the same, so they are a part of lambda up. Analogously, we have lambda down, and this is where we just swap out the R for the L relation. So pictorially, potentially our H classes now get identified across a column compared to the row previously. So these two diagrams, they're not R related, but they are L related and still have the same hat, so they're a part of lambda down. Then we have lambda, the final lambda congruence, and this is where we just drop the R or L condition altogether. And this is actually the join of lambda up and lambda down. So this means our H classes potentially get identified across a row or column as long as their hat is the same. So these two diagrams, they're clearly of rank 2. Their hats are also clearly the same, so they are a part of lambda. But we can also see they're not R related, so cannot be a part of lambda up. And they're not L related, so they cannot be a part of lambda down. So here we can see that this in fact is a true join, it's not a union. There's some pairs of diagrams, for example these two, that are not found in either lambda up or down. And finally we have some mu-based congruences, starting with mu S2, where sort of the name comes from taking the trivial congruence and joining it to the new relation. But in sort of practice, it turns out it's the same as just collapsing H classes in D2, and obviously that's a bit easier to think of. So as I sort of already said, we're just collapsing H classes in D2. So these two diagrams are of rank 2, they're H related, clearly a part of mu S2. And finally, mu client 4, the most complicated congruence we're going to encounter. This is where we take lambda as a starting point and we join on mu client 4. So recall the lambda congruence, collapsing the zeroth ideal, collapsing H classes in D2, potentially identifying them across a row or column as long as the hat is the same. And then in rank 4, within a H class, we have the client 4 action. That's going to give us 4 equivalence classes. In here, I've only drawn 2 because I'm starting to run out of colors, but I think the idea is clear. And again, this gets repeated across each H class, but again, with different equivalence classes. And clearly, this is a client 4 group element, so we can just multiply it by itself for our group action to get back to the identity. So this is part of mu client 4. So that allows me to state the results of my work. But before I go into that, I just want to go into how these results sort of came about. And the short one-line answer is playing around with GAP. So Group Algorithms Programming, a computer software package that is designed to work in these abstract algebra areas. So GAP natively knows diagram monoids and can work with them. And this is thanks to work by James Mitchell, who actually coded up this particular package. But the code for the twisted setting is not actually published or publicly available, and it was also mostly completed by James Mitchell as well as some work by James East. And essentially, I can get GAP to produce the congruence lattices for me. So you might wonder, well, what did I actually then do? Well, there's a big but. And that but is that it only works for very low degrees. So in the Brauer setting, we can only go up to degree 4, and in the Temperley-Lieb setting, we can only go up to degree 6. And that's because of just the computation time becomes too long. It's because any degree that sort of is larger, the number of elements in our mono just becomes too large. And because of that, we can also see, we can get a little higher in the Temperley-Lieb because it doesn't quite have as many elements for the same degree compared to Brauer, say. Okay, so that's a big problem. And also, it only just gives us the lattices, but it doesn't tell you the actual congruences contained in the lattice. But, and yes, I'm aware I'm now in a double negative. I hope you can conjugate. It does tell us where the Riesz congruences are, and it does give us some info about the congruence, which, as I learnt only a few weeks ago when I gave a practice talk of this presentation to my supervisor, James East, that would have been useful to know when I first started working on this, but, well, I know it now. So essentially, what does it give us? Well, this is what it gives us. So if we're looking at, say, the Brauer monoid of degree 3 and 4, so 3 and 4, that's what GAP spits out for us. So it tells us T, the trivial congruence, U, universal congruence at the top, and then it tells us R for some Riesz congruences, and the numbers essentially is just an index on the congruence. So this is the 5th index congruence that it found, this is the 4th one, and so on. So it tells us a bit, but not much. So there is actually still a lot of work to do, which primarily at the start is just guessing, well, what would the lattice look like for any n? So obviously you are hopeful that there is some sort of discernible pattern as n increases, what happens to the lattice, but plenty of examples in maths where a pattern sometimes is not as clear as one would like. And also, well, we need to know what the actual definitions for all of these congruences are. So that now allows me to state the theorem I was able to prove last year, and this is for the Brauer monoid. So for the zero-twisted Brauer monoid, the congruences are all of the Riesz congruences, the group-based congruences, the lambdas, and the mu's. And the congruence lattice is, well, in the odd degree, a simple chain where we find the Riesz congruences interleaved with the group-based congruences as you would expect if you sort of have done any work in this area. And in the even degree, we see this same chain appearing, but we have 3 diamonds at the bottom. And this is where we find the lambda congruences as well as the mu-based congruences. So let's just have a look at this in a little bit more detail, starting off with the trivial congruence in R0. So if I take a diagram, and if I copy the exact same diagram, obviously they're going to be trivially congruent. If I take these 2 diagrams, they're both of rank 0, so they're going to be R0 related. But because they are different diagrams, they cannot be a part of the trivial congruence, and we have a strict subset between trivial and R0. If we say now look at R0 and mu S2, well, let's move R0 across and bring in 2 new diagrams. These are both of rank 2, they're H related, so top and bottom row the same, so they're a part of mu S2. But because they are different diagrams of rank 2, they cannot be a part of R0, which only identifies non-different diagrams of rank 0. And likewise, these are different diagrams in rank 0. Mu S2 only identifies only identifies different diagrams of rank 2. So again, R0 cannot be a part of mu S2. These 2 congruences are incomparable. And finally, let's have a look at RS2 and lambda down. So recall R0 is a subset of RS2. So these 2 are obviously going to be RS2 related as well. And these 2 diagrams are lambda down related because they're rank 2, they're L related, and they have the same hat. But they are not R related, so they cannot be a part of RS2 because they need to be H related. And obviously you can repeat this analysis for all of the different pairs in this lattice. From this result, it's not too much more work to show that the monoid is also congruence permutable, which roughly speaking, if you're not familiar with it, just means you can swap out the order of 2 congruences if you are composing them. In terms of a proof of this result, well, the first step is to show that all the congruences that I claim are congruences are in fact congruences. And then I need to consider every principal pair of, every principal congruence generated by every possible pair of diagrams alpha and beta. I need to show that principal congruence is contained in my list, and then I need to show my list is closed under joins. If I have done that, I then am able to apply a very helpful lemma by East, Ruškuc, and Temperley, and that lemma says that my entire list of congruences is the entire list of congruences for this monoid. To give you a bit of a better sense of all of the different choices of alpha and beta that you need to check, this is a decision tree for the Brauer result, but there is an asterisk here, and that is that this decision tree is slightly more complicated than it is in the actual write-up of the result. And the reason for that is because the definitions I've given you for the congruences are slightly simplified compared to the ones you find in the formal write-up. So there's a bit of a trade-off. You can be simpler in either the decision tree or the congruences, but not both. So first, we check, do we have the same diagram? If so, we get the trivial congruence. So the congruences we're going to get are the ones in red. If they're not the same, well, if 1 is equal to 0, we're going to get the least congruence of the non-zero one. If both are non-zero, if they have different ranks, we're going to get the least congruence of the larger rank. If they do have the same rank, we need to check, are they H-related or not? If they're not H-related, we're going to look at some in both cases, we're going to look at some low ranks. And that's mostly to pick up on the diamonds in the even setting. Over here, we're going to check if they have different hats. That's going to give us R2. If they have the same hat, though, we need to check how are they R or L related, because depending on that is going to give us the different flavors of the lambda congruence. And over here, we need to just take care of the Klein-4 action, which is going to weed out the mu Klein-4 relation from the group-based congruences. The Temperley-Lieb result, well, it actually turns out that the congruence lattice for Temperley-Lieb is a sublattice of the Brauer result. So recall the Brauer result and recall that the H relation is trivial for Temperley-Lieb. So that means all of the group-based congruences, well, they can't exist. They're just going to collapse to the least congruence sitting underneath. And likewise, all of the mu-based congruences, well, they also can't exist because they're based on a H relation. So what we're left with then is just the least congruences and the lambdas. And our congruence lattice in the odd degree is still a simple chain, but this time just least congruences. And in the even degree, that same chain, but with one diamond where we find our lambda congruences. Not too surprising, Temperley-Lieb is also congruence permutable. In terms of a proof of this, well, exactly the same procedure as was the case for Brauer. So the decision tree here, again, we're going to check all pairs alpha and beta. First, we're going to check, are they the same? Again, we get the trivial, then different. If 1 is 0, we're going to get the least congruence. If they're both non-zero, if we are in a different rank than 2, we're going to get the least congruence. If we are in rank 2, as we sort of had in the Brauer setting, if the hats are different, we get R2, but if their hats are the same, we need to check, are they R or L related to pick up on which lambda congruence we have. Now, obviously, visually, this decision tree is much simpler than it is for the Brauer setting, but the Temperley-Lieb result is not a trivial corollary of the Brauer result. And the main reason for that is, even though there's not sort of that many cases to check, the constructions required in the Temperley-Lieb proof are much more sophisticated and difficult to derive because of the no crossing condition allowed, which means the sort of diagrams that you construct and need to be thought of much more carefully, and it's certainly a very non-trivial corollary to the Brauer result. I just really want to stress and emphasize that. Now, I did say the partition monoid would make a brief reappearance. This is it. So the year before my Brauer result, East and Ruškuc looked at the zero-twisted partition monoid, and they found that its congruences are the least congruences, the group-based congruences, the 3 lambdas, and only mu S2, so mu Klein 4 doesn't exist. If you're looking closely, there are lambdas here, and that is because, strictly speaking, these congruences are different to the ones that I defined for you, but in essence, what they're trying to capture, it is the same. So that's why I'm using the same letter, but do just keep in mind they are different. So what is the congruence lattice? Well, we don't have an odd or even degree, we just have all ranks. And we basically get very much the same thing as we do in the even degree for the Brauer, except we only have 2 diamonds. And that sort of makes sense if we think about it, because the 3rd diamond came from the mu Klein 4, which doesn't exist. So we would expect to only get 2. What is noteworthy though here is that we see the lambda congruences sit underneath mu S2, where in the Brauer result it's the other way round. And this is because here we have rank 0, rank 1, and rank 2, whilst obviously in Brauer it goes from 0 to rank 2. Now in fact, this theorem is actually much bigger than I've stated here, and this is for the original theorem is for the entire infinite twisted setting, and sort of it has as special cases of this infinite twisted setting the cases where we have an arbitrary d twisting, as well as the special case we were looking at when d is equal to 0, which is what I stated here. And this whole construction of sort of constructing an infinite overarching theorem and then having the finite cases as special versions of it, this idea is going to be not quite important, but do just keep it in mind for later on. It's going to make a reappearance. Sort of just for completeness, I do also want to mention some non-twisted results. So these are by East, Ruškuc, and Temperley from a few years earlier again. And this is that the congruence lattice for the non-twisted Brauer monoid is they're slightly bit more complicated. We still sort of have this chain at the top like we did before, but at the bottom we have 3 cubes. So this is the even degree, this is the odd degree. And they also covered in the same paper Temperley-Lieb, where sort of similar, somewhat simplification from the Brauer that we just have 1 cube at the bottom, and in the odd degree, 1 diamond. In fact, this paper is sort of quite a large paper. It covers all of these other non-twisted monoids as well. So let's test my memory. Partition monoid, partial Brauer, planar partition, symmetric inverse, Motzkin, symmetric, order preserving. So it is a very big and substantial paper where they proved found all the congruence lattices for all of these monoids. And this is very much actually the basis for the work that I did, is actually starting with these 2 and not so much the partition result from the earlier slide in the twisted setting, because that's slightly different because they were looking at mostly the infinite case, whilst I sort of used this non-twisted setting and sort of added a twist to it. So that brings me to sort of almost the end of the talk. And here I would just like to go over some of the other output that has resulted from this work. Most notably pmdraw, which is a LaTeX package, so PM for partition monoid, and it draws the graphical diagrams that you've seen throughout this presentation, and obviously is used extensively in the proof of these results. So it's designed to be very easy and quick to use, that you don't have to worry about the formatting, you just draw the diagram that you are interested in. But it is also designed to be fully customizable, so if you need to sort of highlight particular things or need to do more advanced things, it allows you to do that. And I'm somewhat happy to offer ongoing support for that. So if you have questions, if you need help, if there's features that it doesn't have that you think it should have, or if you encounter a bug, write me an email and I will do my best to help you out. I'm hoping that this does become sort of de facto drawing method for these diagram monoids, which obviously are used quite a bit in the literature. So how does it actually work? Well, obviously, as is with the case with anything LaTeX, use package pmdraw. And then to draw an actual diagram, well, the simplest is just to draw what's called a brick. And here we need to specify the degree of the diagram we're drawing, so in this example just 4. And then we need to specify the upper non-transversal edges. And in this example, there's not going to be any. So I'm just going to say PMD empty, none. Then I'm going to specify the lower non-transversal edges. And I do this by just specifying the left and right vertex that we are joining. So number 3 and number 4, they get joined. And then I specify my transversal edges. So I specify the upper and then the lower. So number 1 gets linked with number 2, and I have a second edge here, number 2 getting joined with number 1. And that's it. That's simple as you can see, no formatting required at all. You literally just put in the edges that you want, and it takes care of the rest for you. Some of the features I would like to highlight. Well, it can draw concatenated diagrams, so positioning 2 diagrams on top of each other. You already saw that. It has the ability to draw braces and dots, which is sort of if you need to have sort of infinite diagrams or sort of repeating elements. It has the ability to draw labels, so the number 1, 2, 3, 4, for example, we already saw that at the start of the presentation. You can change the formatting of the diagram in whatever way you wish, basically. And for sort of more complex functions, diagrams, you can sort of get a bit lost as to like which diagram, which vertex are you up to. So it has a grid to help you keep track of the coordinates. So all of the ones with stars I haven't explained fully, and that's because they are on an example in the next slide. And also, as you have seen, all of this is compatible with Beamer. Specifically, as you see, I can reveal different bits of the diagram one bit at a time as you are talking about it. So let's look at these examples. To begin with, this is an example that is actually used in the proof, and I think it's a good illustration of the way that this package just allows you to express sort of an abstract idea whilst retaining a good amount of generality, but sort of giving a bit of visual intuition to the reader, and also how you can make use of some color and different shapes to specify or talk about specific bits of your diagram. Now this is an example of the braces and dots. So obviously we're familiar with dots in, say, matrices, and then sometimes we might want to specify, well, exactly how many are there, and that's where the brace comes in. So we can very easily see that this diagram has got rank P. This is just sort of a crazy example for all the different formatting things that you can do. Well, it's not everything. There's plenty more you can do. Just a bit of an overview. You can change coloring scheme of your vertices, change the way edges are drawn, change out specific vertices or edges to different coloring, add extra sort of labeling or pictures on top, multiple vertices. You can even rotate things. Really, it's as good as your tick skills, basically. And this is an example of the grid, so it sort of just helps you keep track of where everything is. So to close off with, well, continuing with the output of this work, well, one aspect that this work has resulted in is an integer sequence. This is published in the online encyclopedia of integer sequences. And this is for the Brauer monoid. And essentially what it does is it takes the degree, so starting at 0, and it counts how many congruences have we got. So for degree 0, we have 2 congruences, degree 1, we have 2, and so forth. Also, there is the same for Temperley-Lieb, but this this sequence is not quite published yet, but it will be published very soon. There's also my YouTube channel, and here you can find a 20-minute version just discussing the Brauer result. There's also a very quick speed talk, condensed version of this talk in 10 minutes, looking at the Brauer and Temperley-Lieb results. There's a 50-minute talk on the Brauer and Temperley-Lieb result where I go into them in quite a lot of detail. However, I would not recommend this for you because you're about 48 minutes into that talk. And there's also a 50-minute talk exploring these other diagram monoids. This is at a very, very basic level and essentially is just designed to give you an overview of the different varieties of diagram monoids and how they sort of interplay with each other. So very approachable, very elementary. So what would be the next steps in this line of research? Well, if you recall, we were looking at the zero twisted variety. So the next step would be to generalize this to an arbitrary D twisting. And also recall that this actually makes it much more complicated. So this is the congruence lattice for the Brauer monoid of degree 4, so it's still very small, and D is only equal to 2, and we can already see how, I'm going to say horrendous that is. It's a major step up in complexity to go from D equals 0 to arbitrary D. Then there was also the infinite twisted setting. So this is then another step up in complexity, but it would be very nice to cover that. And then recall that the partition monoid result from East and Ruškuc, they essentially sort of then had the infinite twisted setting as their big theorem, and then these finite ones as special cases. It'd be really good to be able to replicate that sort of a construction in the Brauer and Temperley-Lieb monoids. So as far as I'm aware, the partition monoid, well, that has been completed by East and Ruškuc, and my work on Brauer and Temperley-Lieb in the zero twisted setting, those two pieces of work, that seems to be it. So there's still plenty of other monoids in here that can have this research program applied to them. So hopefully you have learnt some interesting maths with the help of diagrams.